So thanks for sticking around. So this is joint work with John, who's at Austin, and Scott, who's sitting over there. And this is a paper about the many-to-one matching with contracts problem, in which you have agents in one group, let's call them doctors, who each seek at most one job from a second group of agents, let's call them hospitals. Yeah? This problem pops up again and again in practice, and theoretical research on this problem has been used to design real-life matching mechanisms for applications such as school choice, university admissions, and entry-level labor markets. Yeah? And two goals that are central for designing these matching mechanisms, and that are also going to be central for this talk, are as follows. So first, you want a matching mechanism to be stable, yeah, which requires that agents should never have an incentive to recontract once the outcome of the mechanism has been proposed. The second property is strategy-proofness, yeah, which requires that telling the truth about your preferences is a dominant strategy for the agents. Yeah? And in this presentation, I aim to tell you when and how you can achieve these two goals. Yeah? Now, from the previous literature, we already know quite a bit about when we can satisfy these two goals. So first of all, think about a world of pure matching, in which the only decision is whom to match to, but not how to match to a particular agent on the other side. Yeah? In this world, we know that stable and strategy-proof mechanisms are guaranteed to exist if and only if hospitals view distinct doctors as substitutes. Yeah? However, when we move to the world of matching with contracts, when you have to decide how to match and not only whom to match, then it's no longer necessary that hospitals view different contracts as substitutes for each other. Yeah? And in fact, there's a recent trend in the literature, so there was a whole session at the AAs devoted to these applications, yeah, to uncover more and more interesting real-life applications in which stable and strategy-proof matching is possible, even though the substitutes condition is violated. Yeah? Moreover, in each of these applications, it turns out that the cumulative offer mechanism that was introduced by Gale and Shapley is actually stable and strategy-proof. Yeah? So in light of these observations, I think it's natural to ask the following two questions. Yeah? So first of all, how far can we push this? Yeah? So what's the weakest condition on preferences that guarantees the existence of a stable and strategy-proof mechanism? Yeah? And I should point out that the conditions are going to be placed on the preferences of the multi-unit demand side of the market. Yeah? So in my terminology, on the preferences of the hospitals. Yeah? Secondly, under which conditions are cumulative offer mechanisms, which play a really central role in the literature on matching, yeah? Under which conditions are these mechanisms stable and strategy-proof? Yeah? And it's not only that the answer to each of these individual questions is important, it's also the combination of the answers of these two questions, because if we would get a different domain for the second question than for the first question, right, there might be some other mechanism out there that we haven't yet discovered, which sometimes does the job when the cumulative offer mechanism fails. Okay? So here are our contributions. So first, we developed new notions of substitutes, and also a second condition that I'm going to introduce a bit later, that distinguish, in a sense I'm going to make precise a little later on, between things that are observable, violations that are observable, and violations that are not observable. Yeah, the theme will be that observable violations of these two conditions are always problematic, while unobservable violations can or cannot be problematic. Secondly, we provide a general rationale for using cumulative offer mechanisms, yeah, for settings in which you have matching with contracts, which is that these mechanisms are the only candidates for stable and strategy-proof mechanisms. Yeah, in the sense that whenever there's some mechanism that satisfies these two goals, it has to be a cumulative offer mechanism. Third, we provide the first maximal domain result for the existence of stable and strategy-proof mechanisms in models of matching with contracts. Yeah, and finally, I don't think I will talk about this much here, but we have a companion paper which came out in this year's Papers and Proceedings, in which we introduce a class of applications, which we call matching with flexible allotments, that nests many matching models with distributional constraints, yeah, and for which no previous sufficient conditions apply in general. Yeah? So the conditions we find are strictly more general than the conditions that have been out there before our work. Okay? Any questions at this point? Okay. Yeah? So the related literature slide is at the end. So let me jump straight into the model. So it's the basic Hatfield and Milgram model of matching with contracts. So we have a finite set of hospitals H, a finite set of doctors D, and a finite set of bilateral contracts X, where each contract X has one doctor associated with it, one hospital, and some terms of trade. And these terms of trade can be pretty much anything. The one thing we are going to require is that there's a finite number of possible terms of trade. Yeah? Now, in the future, whenever I talk about pure matching, I mean the case in which there's only one possible term of trade, which is to get matched. Okay? One tiny piece of notation. So for any agent I and any set of contracts Y, I'm going to denote by yi the set of all contracts in Y to which agent I is associated. Yeah? Now, as I said in the introduction, we're going to be focusing on many-to-one matching. Yeah? So a set of contracts is feasible if and only if each doctor signs at most one contract in that set of contracts. Okay? Now, next, let me tell you about preferences. So for doctors, this is going to be very simple. We assume that each doctor has a strict preference relation over all the contracts that he could sign and some doctor-specific outside option. Okay? Now, for hospitals, we're going to encode preferences in choice functions, which tell us from any set of contracts that a hospital could choose from, which set of contracts it would actually like to sign. And here we impose two conditions. First of all, we assume that hospitals always pick feasible subsets of the set of contracts that name them. Secondly, we're going to impose a basic rationality condition, which says that if hospital H is not interested in signing contract X, then its choice shouldn't change when we make contract X unavailable. Yeah? And this in the literature is called the irrelevance of rejected contracts condition, but it's essentially just the rationality condition. Now, what we do in the following is we're going to fix a profile of these choice functions. So we're essentially going to fix preferences of the hospitals. Yeah? And eventually, we're going to find a set of conditions on these choice functions such that a mechanism with certain properties exists. Yeah? Now, it's sometimes actually useful to not look at what hospitals choose, but to look at which contracts the hospital wants to reject. Yeah? And this is summarized by this rejection function. Okay? Yeah? So now that I've described the basic setting, let me describe the properties that we aim for. Yeah? So first, a mechanism, since I'm fixing the choice functions of the hospitals, I'm going to tell you more about this in a second, a mechanism is going to map preferences for the doctors into outcomes. Okay? We say that a mechanism is stable if it always selects outcomes that are feasible, individually rational in the sense that no agent has a unilateral incentive to drop some of the contracts he was assigned to, and finally, the outcome should be unblocked in the sense that there's no feasible set of contracts for which all associated agents have a strict incentive in signing these contracts, potentially after dropping some of the contracts they were assigned by the mechanism. Okay? And a mechanism is strategy-proof if each doctor has a dominant strategy incentive to tell the truth for each possible two-preference relation the doctor might have. Okay? Yeah? So one more word on this. Why do we fix the choice functions of the hospitals and only focus on incentive compatibility for the doctors? So the reason is that it's well known that if you want stability, you can't have dominant strategy incentive compatibility for the multi-unit demand side of the market. Yeah? So that's why we focus on this question. And also, there are many applications in which the scope for the multi-unit demand side of the market to engage in strategic misrepresentation of preferences is actually quite limited. So when you think of school choice, of many entry-level labor markets, and so on and so forth. Okay? Now, let me tell you about the central mechanism in the literature, the cumulative offer mechanism, before I move on to the new stuff. So given a profile of preferences for the doctors and the profile of choice functions, the cumulative offer mechanism relies on the following simple algorithm, where in each round, each doctor proposes the most preferred contract that hasn't been rejected yet. Hospitals temporarily accept their choices from the set of proposals they've accumulated so far and reject everything else, and the algorithm stops when no more new offers are made. Yeah? And then the outcome of the cumulative offer mechanism is the union of hospitals' choices from their final sets of accumulated offers. Okay? Now, this mechanism in general will not be stable and strategy-proof. Yeah? It may even fail to produce feasible outcomes. Yeah? And what I'm going to do next is build towards a set of conditions which are going to guarantee, as you're going to see in a couple of minutes, that this mechanism is stable and strategy-proof. Okay? So as a first step, I'm going to finally give you a precise idea about what we mean when we talk about observable things. Yeah? So first of all, an offer process for hospital H is just a sequence of distinct contracts, all naming this hospital. And we call an offer process observable if at each point of this offer process, the doctor who's associated with the next contract in this process is not currently employed by hospital H when it can choose from all previous contracts in this offer process. Okay? Yeah. Now, note that any offer process that has at most one contract per doctor is observable by definition. Yeah? And note also that you can think of observable offer processes as possible paths of applications in the doctor proposing cumulative offer mechanism. Yeah? So whenever an offer process is observable, you can define preferences for the doctor such that you actually observe this particular offer process when you run a one-hospital version of the cumulative offer mechanism. Okay? Now I'm going to use this notion to introduce a substitutes condition and a size monotonicity condition. So first, we could say that a choice function is observably substitutable if the set of rejected contracts expands along any observable offer process. We say that a choice function is observably size monotonic if the number of chosen contracts weakly increases along any observable offer process. Okay? So let me briefly compare this observable substitutability notion with the more classical substitutability notion. So substitutability requires that the set of rejected contracts always expands when the set of available contracts expands. By contrast, observable substitutability only requires the set of rejected contracts to expand when you can find an offer process that first arrives at the set of contracts Y and contains all of the contracts in Z. Okay? Yeah? Yeah, so in this sense, this condition weakens the substitutes condition. Okay? Yeah? So, any questions about this? Good. So here's our first main result, which is a necessity result. So assume that there's just one hospital H whose choice function is either not observably substitutable or not observably size monotonic, and assume that there are at least two hospitals. Then you can find unit demand preferences for the other hospitals such that no stable and strategy-proof mechanism exists. Okay? Yeah? So in particular, observable substitutability size monotonicity is the weakest set of conditions that could, and could is underlined for a reason, yeah, that could guarantee the existence of a stable and strategy-proof mechanism. Yeah? Now the hard part here is to show the necessity of observable substitutability, but I don't have time to go into the proof. Yeah? Yeah? But I want to point out that actually, if these conditions fail, yeah, there's no stable and strategy-proof mechanism. Yeah? It's not a result which tells you when the cumulative offer mechanism is stable and strategy-proof. Yeah? It's a result about the existence of some stable and strategy-proof mechanism. Okay? Now let me come to our second result, yeah? Which is as follows. So for each hospital H, consider some domain of choice functions for this hospital that contains all unit demand preferences. Yeah? And assume that there are at least two hospitals. Then we can show that if for all profiles of choice functions a stable and strategy-proof mechanism exists, it has to coincide with the cumulative offer mechanism. Yeah? So this is a new foundation for using cumulative offer mechanisms in settings of matching with contracts, which is that they are the only candidates for stable and strategy-proof matching. Yeah? Okay. However, somewhat surprisingly, at least to me, these two conditions, observable substitutability and observable size monotonicity, are not enough to guarantee that cumulative offer mechanisms are strategy-proof. Yeah? They're enough to guarantee that they are stable, Yeah, but they're not enough to guarantee incentive compatibility, which is somewhat surprising because these two conditions essentially tell you that the cumulative offer mechanism is guaranteed to run as if all hospitals had substitutable and size monotonic choice functions. Yeah, so here's an example. I won't go into the details here. Yeah? But the implication is that we need a third condition. Yeah? And since this is a one hospital example, yeah, this third condition will have no counterpart in the literature on pure matching. Yeah? Because if we had a pure matching setup, right, and it's just one possible employer, you never want to lie about your preferences. Okay? So here's that third condition. Yeah? So we say that a choice function is non-manipulable via contractual terms, absent other hospitals, if a cumulative offer mechanism in which H is the only available employer and chooses among proposals according to the choice function CH is strategy proof. Okay? Now, let me point out that this neither implies nor is implied by the other two conditions. Yeah? So it's very simple to find examples. And we can also show that given that choice functions are observably substitutable and observably size monotonic, it's actually sufficient to rule out very simple manipulations to check this condition. Yeah? Simple manipulations of the form that a doctor either deletes his most preferred contract or adds one unacceptable contract to the top of his list. That's enough to check this condition. Okay? Yeah? Now, this condition allows us to show that the cumulative offer mechanism is stable and strategy proof. Yeah? So for all hospitals, the choice functions are observably substitutable, observably size monotonic, and non-manipulable via contractual terms in the sense I just defined, then the cumulative offer mechanism is stable and strategy proof. Okay? Yeah? So two remarks on the proof. So first of all, we can't rely on the structural properties of the set of stable outcomes. Yeah? Because, I mean, there won't, in general, be doctor optimal stable outcome. Yeah? We also can't, in contrast to some other papers that have been out there, we can't rely on constructing an auxiliary economy in which doctor optimal stable outcomes exist. Yeah? This will also not, in general, be true. Yeah? Now, let me point out that this non-manipulability via contractual terms, right, it looks a bit tautological, right? So I require that something strategy proof, and I tell you that something else is strategy proof. Yeah? But the thing here is, we require strategy proofness for single employer economies, right? And the result tells you that if you have strategy proofness in all these different single employer economies, you're going to have strategy proofness when all employers are present simultaneously. Yeah? And what we do in the proof is that we show that the cumulative offer mechanism can be manipulated when choice functions are observably substitutable and observably size monotonic. Then there exists one hospital whose choice function is manipulable via contractual terms. Yeah? Unfortunately, I don't have time to go into the details. So this is a summary of everything I told you. Right? So we have a characterization result which tells you that stable and strategy proof matching is possible if and only if choice functions are observably substitutable, observably size monotonic, and non-manipulable via contractual terms. And I've also shown you that a stable and strategy proof mechanism exists. Then it has to be equivalent to the cumulative offer mechanism. Okay? As I said before, we have a companion paper in which we have a class of applications that are not fully covered by any previously known sufficient conditions. This is all I wanted to say. Just one more thing. So actually, when you want stability and strategy proofness, it's fine to restrict attention to cumulative offer mechanisms. However, if you only want stability, we have an example which shows that it's actually not fine to restrict attention to cumulative offer mechanisms, because maybe there's another great, as of yet undiscovered mechanism out there that sometimes does the job in terms of reaching a stable outcome when any cumulative offer mechanism fails. Thank you.